So our two speakers today are Philip Schwarm and Shengshen Wu. They are both PhD students and researchers at the Institute for Manufacturing Technology and Production Systems. A little bit about the Institute. It is at RPTU, which is a public research university in Kaiserslautern, Germany. The Institute has two departments. One has a focus on manufacturing technology, such as machining and micro and ultra precision machining, and the other with a focus on production systems, of which our two speakers are employed. Their focus is on digital technologies for production systems and sustainable manufacturing. Within the Institute, there are about 50 bachelor master theses that our speakers are supervising within their department and approximately 1,000 exams. Most of their research is externally funded, but they also have many industrial projects. And these are done through cooperative projects with industrial companies, including the project that they will present today. So with that, I will turn it over to Philip, and then Shengshen will come on in a bit.
Okay, then first of all, thank you, Susan, for the nice introduction of us and our institute. So I think we can come directly to today's webinar. So welcome, everybody. Today we will talk about optimizing resource allocation in manufacturing with the focus on job shop scheduling using quantum annealing. Therefore, we want to present our research in this area, which was done in our project funded by the Ministry of Economics of Rhineland-Palatinate, entitled The Use of Quantum Annealing for Process Scheduling in Producing Companies. So in particular, we want to talk about the goal of our project, how did we finally proceed in our project, about implementing the scheduling problems, and what was our calculations on the quantum computer. But first of all, I brought you a short agenda of what you like to present to you today. We will start with the motivation of our project. What is the general potential of quantum annealing in industrial applications of scheduling? Which problems can be addressed and improved by it? Then we will briefly introduce our project. What was planned what was the planned procedure and what aspects were addressed. After that, we will talk about the job shop scheduling, which is a modeling technique that is used for model and finally compute such problems. And after that, we will also show you the mathematical formulations, so of the most important objectives, of the most important constraints that will play a role in the industry. After that, we will go on to the implementation. So how did we compute the job shop scheduling problem on the quantum computer? And then we will show you some results, especially in comparison with conventional algorithms. So, and after that, a nice side effect of our project was that we found new potentials where quantum annealing can be applied. So some of the ideas and implementations will present later by my colleague Shengshen. Yeah, afterwards is a Q&A session planned where we are looking forward to your questions and opinions. So the process scheduling is a very complex problem in the industry, which determines when which products are produced, to what time they are produced. So there are many factors that have a direct influence on the profit of a company. So for example, you prefer short lead times in usual, so that you're able to deliver your products on time to the customer or avoid penalty fees. Challenging in this process scheduling is due to the complexity of the processes. As a result, long computation times are required, which means that changes to something unforeseen events like machine failures or material shortages cannot be reacted to. So in the worst case, it would mean the production have to be stopped. So to overcome these challenges, quantum annealing offers the potential to reschedule these planning programs by a fast computation and implement exactly this short-term planning that is needed in industry. So in addition, the possibility of cloud control of the quantum annealing means that in principle, every company has the option of using these services without having to purchase expensive hardware. This led us to our research questions at the beginning of the project. So what has to be done so that the process scheduling problems are solvable on the quantum hardware? At what point does the predicted superiority of quantum annealing take effect? And what must be done to be able to use them on an industrial level? So this led us to our following procedure. In our project, we worked together with two tool manufacturers and a software company for planning tasks to define our objective investigation. So from the beginning of the project, we had the practical relevance due to the industry-related objectives and boundary conditions. And then as well the cooperation with our project partners with the focus on the serious production. The goal was to compute several problems from industry and make a comparison between classical approaches like meta-heuristics and quantum annealing. The first step in this involved formulating the mathematics in QA compatible problem formulation, which served then as the foundation of the comparisons. For the comparisons, we used several factors, for example, computation times, solution quality regarding certain objectives. And this laid the basis for our comparison for the practicability of our approach. So we wanted to look, can we compute practical planning data and what has to be done to integrate the quantum annealing process into the processes in industry. So our use cases we defined with together with our industrial partners, you're seeing here. We have 4 use case scenario which can be characterized according to 4 problem characteristics. The first one here is the problem size, so to say, how many jobs are handled in one planning sequence, how are they structured in terms of sequences of several tasks. Then we have the constraints, which boundary conditions can be implemented in the manufacturing system, which have to be considered. This involves, for example, the integration of machine failures or in the planning process. Then we have to consider objectives. What objectives are the focus in the industrial environment? What is observed? Are there any priority rules? And last but not least, we have the solution methods. How is the model computed? Are there heuristics used? It's a manual planning? How is the rescheduling done? So our 6 use cases we defined differ in terms of complexity, starting with relative straightforward problem formulation, also known as the flexible job scheduling. And then the complexity is increasing by taking into account various constraints such as rescheduling, setup times, transport times, and then multi-criteria objectives. Leading to the computation of industrial planning data. So in our first step, we have to do the mathematical formulation of our application scenarios. So therefore, constraints and objectives have to be summarized in a Hamiltonian notation. The question was how to do these. So first we have to formulate them and have to assign suitable variables into the desired shape. Therefore, we can use the modeling technique also called job shop scheduling, which I now will further introduce to you. The job shop scheduling problems can be described through a set of jobs that have to be processed in a manufacturing system, where the number of jobs are each built up from several operations or tasks, which have to be assigned to different machines. So each task has different processing times, has other properties like priority. It's depending on the object of interest. So that's already the keyword. There are different types of job shop scheduling problems. In the classical one, which is here presented, you have the objective to consider small snakes. Oh, sorry. I think it's going off.
You're okay now.
Okay. The objective we are considering is the make span. This means you want to schedule all jobs on the machine as quickly as possible. So in order to ensure short lead times. However, the scheduling problem is the subject of several constraints. On the one hand, you have a procedure constraints that ensures that the sequence of operations is followed. There's an overlapping constraint that proves that only one operation is ever assigned to a machine at a certain time. And furthermore, each operation has fixed assignments, which means that each operation has only one machine to choose from which it can be assigned to. So the problem with this classical formulation is, however, in reality, many machines can process several tasks. That means that operations are not firmly coupled to one machine. This leads us to the flexible job shop scheduling, which is a variant of the classical job shop scheduling. Here, what we can see here is here the operations are not directly linked to one machine. Here, each operation has a set of machines on which it can process on. And another representative of the job shop scheduling is the dynamic job shop scheduling, which includes the dynamic events mentioned at the beginning. This means that initial schedules are rescheduled due to dynamic events, such as machine failures or bottlenecks in raw materials, urgent jobs, or machine breakdowns. So the goal of the dynamic job shop scheduling is to map the dynamic characteristics of a real system and to counteract these probabilistic or deterministic disturbances with a dynamic rescheduling. So that's the point. Both the flexible and as well the dynamic job shop scheduling from the starting point of our research. The basis for each optimization problem is the mathematical formulation of the chosen model. In our case, the starting point is a flexible job shop scheduling problem, since we only apply binary quadratic models. Discrete quadratic models or constrained quadratic models to the quantum annealer, we have to formulate our variables accordingly. So today we only talk about the BQM, so the binary quadratic model formulations, since this is used for most the solvers, we can apply it, and also is the base for our iterative solution approach. So to allocate a specific operation to a specific machine, we also have to use a time range within the operation can process. So therefore, we have to assign to each possible allocation of an operation a machine in an additional discrete time step. This procedure is shown here on the right side. There are the binary variables for each allocation is equal to 1 if an operation is processed on a machine at the exact given time and 0 otherwise. So this leads according to the problem to a variety of variables. In particular, we have O times M times T variables in sum, which is the product of the operations, machines, and times we are choosing for our model. So it's we can see here that the that we also will need variable planning techniques to effectively reduce variables and calculate large problem sizes. So these binary variables are then used to add to various constraints and objectives to our job shop scheduling model. And the first constraint we want to talk about is the procedure constraint, is a processing constraint, which applies only in binary variable modules, because the variable are designed in such a way that each variable determines a time and the machine at the same time. It can happen that an operation is assigned several times or to a time or several times to a machine by assigning the specific variables to equal to 1. So to prevent this, the so-called processing constraint is used, which is visualized here. Here you can see our typical time looks like, the time range looks like from which an operation can be assigned. So each square here stands for a specific time on a machine. And here the timeline is just printed twice for the understanding. To prevent an operation from starting again, every possible start time is set in a quadratic relation with every other possible starting time on the same machine. So this is illustrated through the blue arrows here. And as we can see here, we have the same operation starting multiple times, will lead in our model to a higher energy value. That's the first constraint we have to consider. Then we have a second constraint. It's called the procedure constraint, which carries weighting when 2 consecutive operations are not processed in the predefined order. Here I also brought 2 schedules. The first one here, it's fine. The operation 1 starts before the operation 2. But in the schedule 2, you can see the operation 2 starts before the operation 1. So this results in an increasing energy value due to the quadratic linkage of the different times. Here all times are connected, also like the constraints before, with the quadratic interaction. So then we have our third constraint. It's overlapping constraint, which takes non-zero values when multiple operations are scheduled simultaneously on one machine. So therefore we have here again a time interval of 1 machine illustrated 2 times. So we can see between operation 1 and operation 2 we have no overlapping. Here's everything fine. But in the to operation 2 and operation 3, we have one overlapping to this time, and this leads also to a quadratic interaction, which leads to a higher energy value here. So now we formulated our constraint from the classical flexible job shop scheduling. And we have also to formulate our first objective. As mentioned before, in the flexible job shop scheduling, the make span is the most commonly used objective, which assigns higher weights to late start times of jobs. So low start times are intended to be achieved. To integrate make span into BQM formulations, operations, so must be forced to start as early as possible. which is done by assigning weights to the gaps between two operations. What you can see here is we have operation starting at the time 2, and we have the second operation starting to time 8. And in this case, according to our procedure constraint, the operation 2 could have started at the time 5. And so the makespan objective is here assigning a linear increasing weight how for each time step it's away from the optimal time it could have started. So we can here see in the stage if it attain 5 as the variable, it would attain an energy value of 0 and so on, and then in the 6 you would let's see 1, 7, 2 and 8, 3. And so in our case, we have then the different energy values according to the different starting times. And using the constraint and the objective, we can now compute again. We can now use the constraint and the makespan to compute the flexible job shop scheduling problems. But before we come to the computation, we need to talk about the limitations of our approach. So the classical quantum annealers are still limited by the number of qubits they have available. This means to compute large problem sizes, we have to calculate the problems in different steps. So we can either divide the problems into subproblems, or we can compute one by one with hybrid algorithms. So on the left side, you can see a simple procedure that we are using in our approach. We first determine the number of jobs and operations we have to process in one loop. Then in the second step, we have to compute a bottleneck factor that indicates the priority of the subproblems according to the chosen objective. For example, the makespan objective would prefer long subproblems with long processing times. Then in the next step, we have to solve the subproblem, and after solving the subproblems, we can continue with the computation of every subproblem, and after that we can merge them together to a solution. And this is done in our case by also a hybrid solver, which is called Kerberos. You can find them in the D-Wave library. And in our case, this is a combination of a hybrid workflow using quantum annealing, simulated annealing, and taboo search. And now we can come to our first results. What you see here is the computation of several benchmark problems from literature. We also published it in the Journal for Production Engineering. Here we computed 10 different problem sizes, called the MK problems, with our iterative approach in blue, and DQM approach, so the discrete quadratic model approach in orange. And on the left side, you can see the results regarding the makespan, and on the right side, the computing times of the approaches. What you can see is on the solution quality. So to say, the makespan minimization only slightly differs from the benchmark problem sizes. On the other side, we have achieved very small computation times with the iterative approach. So nevertheless, it has to be mentioned that in this figure only the annealing times, so the access time to the quantum annealer is shown. But however, according to this first results, the quantum annealing has shown potentials for the industrial applicability. because of the very small computation times achieved here, and which are required for the responsiveness of the manufacturing system. So, which is why in our recent work, we enhanced our formulation for the job shop scheduling problem. In this context, real constraints of the manufacturing system were taken into account. Firstly, jobs of the have a priority. Then, then each job has due dates that need to be considered. Constraints, that have to be considered. I include setup times, transport times, and the dynamic events described earlier. And furthermore, we want to consider more than one objective at once. Therefore, we implemented a tardiness minimization objective, a priority objective, and as well a workload minimization objective. The aim was to adapt the previously very theoretical problem to an industrial reality through the integration of various objectives and constraints. And that's the point. I will hand over to my colleague Shanxian. And Shanxian, you can.
Okay. Thanks for Philip. And I would like to introduce the rest of our work. So first of all, I want to present the mathematical formulation for 3 additional objectives in detail. The first one is workload minimization. This objective aims at to minimizing the unitization of the machine, which means the workload of all the machines should be minimized. It is related to the processing times of each operation, because in the flexible job shop scheduling, each operation has different processing times for different selectable machines. The operation should choose the machine that has minimal processing time. The punished value is related to the difference between the current processing time and the minimal processing time. For example, here, operation 1 has 3 selectable machines and different processing times. Machine 1 has the longest processing times and machine 3 has the shortest processing times. So the first solution, which is the assignment on the machine 3, has the lowest energy of 0, and the solution is optimal because the process time is shortest. And for the solution 3, although the processing time, although the operation 1 is finished earlier than in other solutions, however, the energy value is 2 because the processing time is longest. And the second objective is timeliness objective. Timeliness objective is to minimize the late jobs, which means that the finish time, the late job, which means that the finish time of the job is later than the due date. Because in manufacturing system, each job has the due date, the delivery time. And the timeliness is not related to how earlier the job finished. It's only related to the jobs which is later than the due date. So, for example, here, we can see that there are 2 jobs with different due dates. The green bar is job 1, the last operation for job 1 with due date of time step 5. And the bar with the hair green is the job 2 with due date of time step 10. And in the solution 1, there is the time gap between 2 operations, but the energy value is lower because the 2 jobs are finished before the due date or on the due date. However, in solution 2, the job 2 are finished fast 7 time step earlier, but because the job 1, which finished later than 1 time step later than the due date, so the energy value is 1. And for the second objective is priority objective. This objective is aiming at following the priority rules. The jobs with higher priority should be finished before the jobs with the lower priority. However, in real manufacturing system, the priority rules cannot be considered alone, must be considered by the timeliness objective or the mixed-span objective. And for the iterative approach, the priority rule should be considered together with the early finish time, which means there is no gap between different jobs, and the jobs should be finished as soon as possible, which means the operation should be started after the processor time. So what is processor time? So what is processor time? Is the sum of the minimal processing times for the previous operations. And then in this example, there is a job 1 with the higher priority 2 and the job 2 with the lower priority. So the optimization, optimal solution is here. The job 1 is finished earlier than the job 2, and there is no time gap between them. And for the solution 1, if the job 2 is finished earlier than the job 1, there was energy value of 1. And when there is more time gap between them, such as in solution 2, the energy value will be 2 times higher. So we can see that these 3 objectives actually has conflict. So what happens when these objectives are considered at the same time? Sorry. Yeah. We can know that many objectives are conflict if one objective value is better and the other objective can be getting worse. So quantum annealing approach can realize the optimization of multiply objectives with controlling different weights for each Hamiltonian function for each objective. And it is very hard to directly evaluate the quality of each solutions, because it's not like the single objective function. We can see that if the which solution is better than the other solution, because for a solution, some solutions can has the better in one objective has the better value, and some solutions perhaps and in another objective has the better values. So we need to get we used to evaluate the solution quality by evaluate the performance of Pareto funds. So what is Pareto funds? The Pareto funds is the list of the Pareto solutions. Refer the solution into a multi-objective optimization problem where no single objective can be improved without worsening at least one of the other objectives. For example, here, we considered 2 objectives. One is the common objective, the minimization of mixed-span. The second one is the minimization of workload. And the figure on the left side, we can see in this figure, the red points are the solution of the single objective optimization. And the green points is the Pareto solution, and the blue one is the other possible solutions. We can see that in compared to the Pareto points, the both objectives of the other possible solutions are worse than the Pareto points. So, and to compare to the Pareto points, we can see that if we want to improve one objective, such as one solution, such as workload, if the solution has the better workload, and the max span of this point will be worse than the other solution. So this is what is the Pareto points. So after getting all the Pareto points, we can control the weight of the Hamiltonian function to determine the priority of our different objectives, because this is very important in the real manufacturing system. Because in the real manufacturing, the companies need only one solution. They don't need. They didn't need too much solutions. So for the multiple objective optimization in real manufacturing, it is direct for the company to indicate the priority objective to determine the specific solutions. Okay, the next slide. So what happened? So next, to evaluate the performance of quantum approach to multiple optimization problem, we computed 3 objectives in different combinations. The first is the max span minimization with workload minimization. And second is the minimization of max span with the priority rules to minimize the jobs which not following the priority rules. And the third one is these 3 objectives are considered. And so, and 2 figures on the bottom left side to show the Pareto points obtained by quantum and the classic approach for one problem instance. And the curve in blue is our quantum solutions. And in yellow is the classic solutions. And from the and our objective is order minimization. So if the Pareto points which near to the coordinate circle, which means the Pareto point is better, which has better performance. So it is clear according to the left figure, we can see that the Pareto points obtained by quantum approach has better performance compared to the classic approach. However, in the right figure, it is very hard to determine which solution is better. So there is also a lot of evaluation methods to evaluate the performance of Pareto points. One of them is the C-matrix method, which is suitable for the comparison of 2 methods. The larger symmetric value obtained by one method, that means this method can obtain more better Pareto fronts than another. So we can see that the 3 figures on the right side is all the result for C-matrix for each problem size, which is the benchmark data from the literature and we can see that it is obviously the quantum approach, which is showing in the blue curve, has the better performance because the C matrix value is larger than the obtained by the classic approach. And for the computing time, we have used the two standards for the comparisons. One is the QPUSS time. The other is the total computing time, which means is the time difference between the receiving the solution and the submitted problem on the quantum annealer. And so we can see that the computing time of the D-wave quantum computer consists of internet latence and the service time. Service time, which consists of the QPUSS time and the pre-processing time. And here show an example for computing the one problem size with 15 jobs on the quantum annealer. We can see that the QPUSS time is in 1 second, and the service time is also faster near to 1 second, which means is that the pre-processing does not take so long time. However, the internet latence takes fast more than 1 minute. So the computing time is fast. Not 1 minute, it's near to 2 minutes. So that's why we use two standard for the comparison of computing time. And on the right side, there is the figure for the comparison result for the computing time from the quantum approach and the classical approach. We can see that for the green curve is the annealing time, and the blue one is the total computing time from the quantum approach, and the yellow one is the computing time from the classical approach. And it should be noted that the y-axis is in the logarithmic scale, and the first two problem instant MK1 and 2 are the smallest problems among 10 problem instance. So we can know that for the fast relative large problem size, the quantum computing has the less computing times than the classic solver. And it has consistent short access time to fast in 1 second. Okay. And for the dynamic approach, in real manufacturing system, there are often some unpredictable events, such as a new job arrival or a machine sudden breakdown. So we also implemented the dynamic approach with quantum annealer to react to the dynamic events. So the dynamic job shop scheduling should create a new rescheduling directly in response to the dynamic event to reduce the impact for the dynamic events. So here show the single framework, and for better understanding, I'd like to present an example to show how rescheduling works. Here, at the beginning, we need to give the initial plan schedule, and here is 10 jobs, and with the gray bar is the maintenance time, which no operation can be processed on these times. And then, if a dynamic event occurs, here is a new jobs added to the systems, and the time points is timestamp 5, which showing the vertical dotted line. and all the operations which had already started before this time step should be removed from the scheduled jobs. And the bar in dashed lines shows the initial plan. And then the rescheduling starts. So there is a new reschedule plan. This process will be repeated, will be performed repeatedly, and even if another dynamic event occurs. And the initial plan will be updated according to the times. Yeah. And in real manufacturing system, it is also important for the rescheduling effort objective, which means to minimize the difference between the initial plan and the rescheduled plan, which will cause, because in real manufacturing system, if there is large difference between the schedule plan, the initial plan and the rescheduling plan, it will cause the problem of the stability and to take more time for the reorganization. So here is the scheduling effort objective. Okay. So if there is the difference between the changed machine or the changed time in the starting time, they will be punished. And to validate our approach, we also computing with the industry data, which is from our industry partners. Here it shows a simple framework. We can see that the industry data, the form is some different from the benchmark, which from the literature. Here, the delivery time, the due date is showing date, not showing value. And we can also see that there is a great difference between different processing times. Some operation can be finished in 1 second and the other needs more than 2 hours. So it is very important to data conversation and the time discretization and to select a suitable time unit to reduce the unnecessary variables number. And then the approach is same to input the convened data on the quantum annealer. The mathematical modulation will be automatically generated, and then the solution will be showing in a visualization. And at the end, we also need to convert the solution into the required data from the industry. So we can see that in the industry data, there is very large data, which is larger than which we computed before the benchmark data. We can see that for each machine, there is more than 2,000 operations. And we use the binary quadratic model. So which means one binary variable presents the one operation on one machine and has one starting times. So how many variables for 2,000 operations and with fast 30 machines, and we can also see that there is a large difference between the due date. First, the difference is more than 6 months. So for the performance evaluation, we abstracted a part of them. And we can see that there are 2 problem size. The tiniest is showing days, so there is no difference between the result quality. But quantum annealing has less computing time as the classic approach, because especially for the problem size with more than 200 jobs, the computing time is half of the classic approach. Okay. And this is for the time discretization. This is the time discretization is related to different different processing time for each operations. And here is a very complex mathematical formulations. But it's to simplify that is that the time step is related to different processing times, and the time range for each loop, the estimate time, is related to the sum of the processing time for each jobs and the parallel machine for the same operations and the number of the operation which in the loop. So in short, I will say that by computing the industry data, we can see that there is the limitation. And according to our industry partners, we know that for the short-term rescheduling, the rescheduled plan should be, the computation time should be less than 15 minutes, which can not irresponsible to the dynamic events in time, but also can take the time for the reorganization. So for our current approach with the current capacity of the hardware, the limitation for the job number and operation number is 500 jobs with 50 operations with 30 machines. And there is also limitation from the large difference in processing time ranges, which means if the minimal processing times in second, the maximal processing time cannot be more than 1 day. So it is also important for the first step for the industry exploitation is to coordinate the processing types, and then to create an interface for the automated of planning relevant informations. And the third one, because many companies has applied existing system for the job scheduling and the production management. So it is also necessary to integrate a comparative metric for parallel use of quantum annealing as an assistant system. So here is our software demonstrator, which is suitable for the user who has no experience. The user can select the problem size and the objective here, and the parameter for the weighting for the conjugate can be automatically input. And after enter all the related parameter, the visualization and the result will be obtained on the end. Okay, let's start to the end. In conclusion, our work has implemented quantum annealing for different job scheduling, which includes the multiply objective job scheduling and the dynamic job schedulings. And according to the result, quantum annealing shows the advantage compared to the classical approach. But there is also the limitation in industry application through the current hardware capacity. And so in the future, we will use the integrate advanced technology like deep learning to improve our current approaches, which for the time discretization and to give the estimated time from the deep learning. And in the future, there's also some potential application in industry, such as the layout planning, which determine the optimal position of the machine to minimize the transport time, and the optimizing the resilience in manufacturing system, which means is to select optimal strategy to reduce the disturbance in manufacturing system, which means if the lever cancelled, if there is failure in the machine or there is power failure, how to determine a strategy, such as to use the production from the storage to deliver to the customers. Okay, that's all from my side.
Great. Well, thank you so much. Very comprehensive. Philip, if you want to come back on, we only have time for a couple of questions, but I will send all of the questions to our presenters and ask them to respond via email if they can. Philip?
Yeah.
So here are a few questions that I'll pick out. How did you reform? Oh, and Shin, please stay on camera as well. Let me change this so that hopefully you'll both be there. Anyway, how did you reformulate the constrained optimization into an unconstrained optimization problem like Cubo or icing model? If you have embedded them as penalty terms in the cost function, how is the penalty coefficient conventionally represented as lambda estimated?
So, yeah, first of all, we represented our constraints by applying Lagrange parameter to them. So according to the literature, you have to set the constraints with a higher rate than the objectives. Also, we also did this in this way. So, for example, for the first example we showed here, so the ratio of our objective to the constraints was 1 to 100. So maybe that's one point. And sorry, the second part of the question, maybe you can repeat it, please.
If you have embedded them as penalty terms in the cost function, how is the penalty coefficient estimated?
Yeah, that was try and error because there's no literature we could use to estimate our coefficients. So we have to try it out. We have done many runs on the quantum computer to estimate the right rates for our constraints and objectives.
Okay. Are we to assume that all machines have the same capabilities? In our facility, we use a multitude of machines with different uses and functions.
Yeah, in our model, we also consider that. So we do not only the considering a flexible job scheduling, which means you have only sets of machines on which a specific task can be processed on. So you have to think about it. It's only a model. So you have to attain your model specific to your constraints. So you can say, okay, let's have this task. You have task, and it can be done on machine 1, 2, and 3, and the other task you can do on a machine 4, 5, 6. So that's a thing you have to do before you can calculate or compute your problems.
Okay, and the last question we have time for is it possible to provide a link to the CSV file of industrial data used? Is that publicly available or not?
The public, the CSV file of the industrial data is not publicly available, but we will write another publication where we'll anonymize the results, and then we can forward it. So
Great.
We have to wait a little bit, and then in the next publication we will upload the data as well.
Wonderful, thank you. So to sum up, we have recorded this session. We will be sending out links to the presentation and to the recording within a week or so to everyone who registered. Thank you so much to our presenters. It was just so informative and great work on both of your parts. Our next webinar is going to be Quantum and Finance, and the date, I believe, is December 7th. So you will get an email from us regarding that as well. So again, thank you everyone for attending, and have a great day.
Thank you. Bye.